This is continuation on probability. Last time we looked at contingency tables. This time we're going to learn about something called trees. Trees are used for dealing with sequences of events. Consider the scenario. Suppose that there are 20 batteries in a drawer. Of those, 16 are good and 4 are dead. I grab 2 batteries, one at a time, from a drawer without looking. Now, effectively, it doesn't matter if I'm drawing them one at a time or both at the same time, but for visual purposes, let's just think of these happening one at a time. What combinations of events can occur? Okay, so I'm just going to start kind of branching things out, sort of like a flow chart here, to think about what can happen. So this first battery can either be good or it can be dead. So I have good and dead. Second battery, even if I got a good one on the first pull, I could still get a good on the second or a dead on the second. Second pull, even if I get a dead on the first pull, I can still get a good on the second or a dead on the second. So let's look at all the possible sequences of events that we can have. This will give us our sample space. And our sample space is the set of all possible outcomes. So one thing I have is good on the first and good on the second. That's that top sequence. Let's look at this sequence. That's a good on the first, and that's a dead on the second. Let's look at the next one. Dead on the first, but good on the second. Let's look at this last one. Dead on the first and dead on the second. So that's my list of everything that can happen. Sample spaces are usually written with the Greek letter omega, and they have the set bracket curly start and end parenthesis bracket thing going on to it, but it's just a list of everything that can possibly happen. So let's look at another sequence. This time, instead of pulling 2 times and kind of taking whatever I get, I'm really just trying to actively get one good battery. So I'm going to keep pulling until I get a good battery, or I'm going to stop at 3 because I've had enough. I'll just go to the store and buy a new one at that point. Not really, but for the purposes of this activity. Okay, good on the first. I would stop after getting that good battery, so my sample space here, that's one thing that lives in here, just that good on that first pull. I could have a dead battery. If I have a dead battery, I would pull again, and I can get a good on the second, in which case I would stop. I've gotten that good battery, or a dead on the second. So this stops at a dead on the first and a good on the second. So I could have good on the first. I could have good be the second battery. I can have good be the third battery. So that means the first 2 were dead, but the third one works just fine. Or maybe dead, dead, dead. I have 3 dead batteries, and then I call it a day. So in example 1, follow-up question might be, well, why don't I have the probability of getting 1 good and 1 bad be 1 out of 3? Because as far as I can see it, you could either have 2 good batteries, you could have good and dead, doesn't really matter what the order is, or dead and dead. So it feels like there are really 3 things that can happen. I either have 2 good, 1 good, or no good. So why isn't this probability 1 out of 3? Well, a couple reasons. First off, if you look at it above, you see that it's not really even a 3 as a reasonable answer because I have order matters. And the second thing that makes a difference here is when I'm looking at this tree, I should really be thinking about the weights of it. There are 16 batteries that are good. So this first set, that's 16 out of the 20 batteries. The dead, however, are only 4 out of the 20 batteries. So when I'm looking at each of these pass along, they don't all have the same weight. I'm much more likely to end up with good, good than I am dead, dead. So order matters. And the other thing I have to be really careful about is I have to keep track of changing weights and probabilities. And a tree can do that for me. I'm already seeing that here, where I have 16 out of 20 for this good and 4 out of 20 for this dead. Well, if I think about the next pole, I have one less good battery. If I have one less good battery, that means I have 15 left. And that's out of 19 because I've taken one away. And likewise for the dead, if I've pulled out a good on the first pull, I still have all 4 of the dead ones still left in the drawer out of 19 that remain. So I can see sort of the weighted paths here and how it's way more likely to go where the higher numbers are instead of where the lower numbers are. Looking at the bottom, suppose that your first battery that you pulled out of the 20 was a dead. Now, one thing that might help you is write what changes here. If you pull out this dead battery, the good doesn't change at all. The dead batteries, this goes down by 1. As a result, the total would also go down by 1. So if I pull out a dead battery, I still have all 16 of my goods left. If I pull out a dead battery, I've taken away 1 of the 4, and I have 3 left. You may have noticed this up here, but sets of branches add up to 100%. So both of these things are out of 19 batteries. I'm going to formalize this process, but this is essentially the crux of this entire lesson that we're going to be looking at. We're going to make these trees, and we're going to see how the likelihood of good is significantly higher than that dead. Okay, I'm going to make exactly the same tree again. So I'm going to have same numbers, same situation, everything. I'm just going to talk out all the steps in more detail. So we can assume that the probabilities have the same probability throughout, and I have to keep track of those changing probabilities. So I'm going to make the tree where I can keep track of my events, and each set of branches represents a conditional event. So this is what can happen for the first pull. And on the first pull, 16 and 4 were my respective counts. Now I'm going to write in some notes here for myself. After this has happened, this means I have taken away a good battery from that drawer. And if I'm only looking at the top here, this means I have not changed, +0 or no change, to the dead batteries at all. So when I'm asking myself, well, what can happen on the second pull? Good has gone down by 1. It was 16, it's now at 15. My number of dead has not changed. It was 4, it's still 4. I had 20, I took away 1, it's out of 19. I had 20, I took away 1, it was the good one. I'm out of 19. Now I'm considering a different what if. So down at the bottom, this time I'm assuming that I pulled out a dead battery. I can still get a good or a dead on the second pull, but I have 1 less dead. It used to be 4, and now it's 3. I've taken away a dead. I've not touched the good, so I still have 16. I had 20, but I'm taking away 1, so I have 19. If I want to label these probabilities on the side, and I'm only going to do it on this one just so you can sort of see what's going on, this probability here represents the probability of a good on the first pull. When I'm talking about these numbers on subsequent branches, this is the probability that I get a good on the second, assuming that I got a good on the first. This probability that I have here, for example, this is the likelihood that I get a good on the second if I started out with a dead battery on the first pole. And you can see how the probability of getting a good battery really depends on what that first pole looks like. It is keeping track of those changing likelihoods. This is how I make the tree. The second part is how I use them. So if I want to know the probability of good, this top sequence of events, I find this by multiplying the probabilities along the path. So multiply the path. So for example, the probability of good on the first and good on the second. I'm going to multiply the probability of good on the first times the probability that I get a good on the second, knowing that I got a good on the first. So for the numbers, good, that's up here. I'm going to mark it. I'm going to multiply the numbers that get me there. 16 out of 20 and 15 out of 19. I'm going to type that into a calculator, but that's my answer for the probability that they are both good. And this gives me 63.2% or so. Next one, I have the probability, and I'm going to do this with a star with the box for this one so I can find it easy, that they're both dead. So dead on the first and dead on the second. So dead on the first and dead on the second, that's down here at the bottom. 4 out of 20, that's dead on the first pole. 3 out of 19, that's dead on the second pole, assuming that I've removed one of those batteries. And finally, it says 1 good and 1 bad. I'm going to do this with a triangle symbol. So 1 dead and 1 good. The problem with this is it happens in 2 different spots in my tree. Good and dead, or dead and good. Whenever it happens in more than one spot in your tree, you're going to add up all of those different ending spots. In my 2 different sequences, I had good and dead, and I had dead and good. So I find everything that works. If there's more than one thing that works at the end of the tree, and I add them all up. Okay, let's check this out. Good, 16 out of 20. Dead, 4 out of 19. Dead and then good. Dead, 4 out of 20. Good from the dead, 16 out of 19. I didn't type my last answer into a calculator. Let's type both my last answer and my current one into a calculator and see what we get. I have 4 divided by 20 times 3 out of 19 for my last one. I get 0.032 or so. And for this next one, I'm typing that whole thing into my calculator. And when I do so, I get something like 33.7% or so. Now, just a quick observation. I didn't need to do all of this work to find this last one, because you should actually notice that all of your probabilities add to 100%, or at least approximately 100%. Because in this case, if I add 0.632 plus 0.032 plus 0.337, I get 100.1%. That's pretty dang close. So this gives me a fast way to double check these numbers. These 3 values should add up to 1 or 100%. Let's try another tree. 20 batteries, 16 of them are good, the rest are dead. I'm back to drawing one at a time until I get either a good or draw 3 batteries. So the first is either good or dead. If it's good, I don't keep pulling. So one of the spots where my tree can end is at just that letter G there. If it's dead, I keep going. I'm pulling until I get either a good, which I could get on the second pull, or until I do 3 pulls. I don't keep pulling, I keep pulling from here. I don't stop here because it's a dead battery. If it's dead, I can either get a good on the third, or I can get a dead on the third. Now this one I would also stop at, because I stop until I get 3. These stop at 3. Or good, these stop at good. I want you to try pausing the video and see if you can go in and add the weights for all of these different sequences of events. Assuming that you paused it, let's add it together. Good, 16 are good out of the 20. That means the rest are bad. 4 out of 20 are bad. I removed one of the dead batteries. So that means I have 3 of the dead left out of 19. I've not touched the goods if I'm on the sequence down here, so I still have all 16. I've now taken away 2 of the dead batteries out of the 4, so I only have 2 remaining. If I start out with 20 and I've taken away 2 batteries, I'm down to 18. Sets of branches always add up to 100%, so if I have 2 out of 18, this should be a 16 out of 18. But this also makes sense because I still have all of those 16 good batteries. I've not touched them yet. Language on this one's a little bit tricky, but let's see what's going on. Calculate the probability that none of the batteries pulled are bad. So let's consider all of our ending spots here and try to find any of them that have no bad batteries in it. Clearly, this is not part of it. That has 3 dead batteries. This doesn't work. It has 2 dead batteries. This doesn't work. It has 1 dead battery in that sequence. This doesn't have any dead batteries in it. It looks like the only sequence that worked here. If none of them were bad, then that must mean I pulled a good battery. What's the probability that I get a good battery? Well, that's 16 out of 20. That's 80%. The next one, what's the probability at least 1 is bad? So what's the probability that at least 1 is dead? So let's label these things with the number of dead batteries up the top, just so you can see what's going on. This good, this had 0 dead batteries. Dead and then good, that had 1 dead battery. Dead, dead, good. That had 2 dead batteries in that sequence. Dead, dead, dead. That had 3 dead batteries in that sequence. So when I'm looking for at least 1, that's these sequences that I am combining together. So I've got, looking at the letter sequences that get me to these spots, D and then G. And when I start to do a lot of these things, I don't write down the subscripts as much. I just write down the letters. D, D, and G. If you would like to still keep writing the 1s and 2s under these, that's totally fine. D, 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 that's my third one. Let's have the probabilities. To get to DG right here, 4 out of 20, 16 out of 19. That's the path to get there. Next sequence here, dead, dead, good. I'm multiplying these 3 numbers. 4 out of 20, 3 out of 19, 16 out of 18. here. Dead, dead, dead. The three bottom numbers. 4 out of 20, 3 out of 19, 2 out of 18. I'm going to type this into my calculator and I'll see what I get. And it's a little bit labor intensive, but we'll see what happens. Looks like I get 0.20 or so. Oh, interesting. On the last problem, I got 80%, and on this one, I got 20%. It looks like these are adding up to 100%. Let's see if I can figure out what's happening there. None of them are bad. So this was the situation for equals 0. At least one. This was one or more. And I'm noticing that these two situations are kind of opposites of each other. In other words, the probability of 0 is 100% of all the outcomes take away the situation where I have one or more. Again, I'm going to show you what's going on here. 0 is the opposite of these three things. Another way to phrase this, if I wanted one or more, 1, 2, or 3, I want everything in my tree, 100% of my tree, take away the only situation where I had 0. If I did this on this last problem here, and I did 100% take away 80%, this would have been a much faster way to come up with 0. This subtraction trick is called the complement. The complement of an event is everything in the sample space except for that event. So the opposite of one or more is none. So for example, if I go bowling and then I come home and my partner asks me, how did bowling go today? And I said, I got the opposite of one or more strike. They'd be like, oh no, this means they got 0 strikes. Sometimes it's easier to do subtraction of one thing instead of adding a whole bunch of small pieces. So the complement, I use the little symbol of C to mean opposite or complement. And I'm going to practice that as well. Anything I introduce, don't worry, we will look at more than one example of it. 30% of students take on classes online. What's the complement of this? So online complement, this is, not to be too cheeky, but not online. So maybe that's a hybrid class. Maybe that's face-to-face. Maybe that's remote, depending on how you define remote instruction. What is the probability of the complement? Well, if 30% of students take classes online, what percent of students take classes that are not online? So 30% do. What percent don't? Go ahead and pause the video and see if you can figure that out. 30% take them online. What percent do you think do not take them online? And if you're thinking that through, I think you might have gotten 100 minus 30%, or 70% do not take classes online. Let's look at a scenario and see what we can do. 30% of students take classes online. Of those that take classes online, 60% pass. Of those that do not take classes online, 75% pass. Draw a tree for this scenario. I see two events in this sequence. So first thing, the student signs up for the class. So the first step in this sequence is they've decided to either take the class online or not online. 30% take the class online. which means the rest of them, sets of branches add up to 100, do not. After signing up for the class, at the end of the term, the student has either passed or not passed, pass complement, the course. And that's true if they take it online or not online. Let's fill in the probabilities for these next sets of branches. If they take it online, so whenever you're moving in a tree, you should think if blank or out of blank. If they take it online, 60% pass. If 60% pass, what percent don't pass or pass complement? Great, I've got 40% there. If you do not take classes online, what percent pass? Well, looking at the sentence, 75. If 75% pass, what percent do not pass? 1 minus, that gives me 25%. I can fly through these because I've done hundreds and hundreds of examples of them. The way to get better at probability is to draw pictures and just try it out. You might not get it right on your first guess. That's okay. Just see what you do and make progress and learn from your mistakes as you go along. Education is not always a straight path. Sometimes we have to try things out and learn along the way. What is the probability that a randomly selected student passes their class? Well, let's see where this is in my tree. If they pass, they can either be online and passing. So one option is my online and pass people. Or I see another spot here. They could take it not online and they could pass. Before I try to do any of this in a calculator, let's think about a reasonable estimate for what's going on. 60% of one group passes, 75% of another pass. I'm looking at a weighted average between these. So I'd expect the pass rate to be something between 60 and 75%. Let's use the tree and verify. Online and pass. 30% and 60%. Not online and pass. Not online, 70%. And pass, 75%. I'm going to type this into a calculator and I'll see what I get. Again, I'm expecting this to be between 60 and 75. Given that more people take classes not online, it's probably going to be closer to the 75. If I had to guess, maybe like 70 something. And I will hit enter. Great guess. 70.5%. So the probability of passing a course, regardless of the modality of the course, is 70.5%. If you select a student that passed their class, ooh, I hear an if statement, okay. In the back of my head, I'm thinking this sounds a lot like out of. If you select a student that has passed their class, what is the probability that they take it online? I'm going to use my conditional probability notation because this stands for given or out of. So whenever I'm told something about a person or about a group, that's coming after this vertical symbol. And this is determining the denominator of how I'm setting things up. So out of pass, I am going to be dividing by all spots of the tree where pass shows up. And from this group, let's just start out with this part. The bottom of my fraction is going to be all the spots where someone has passed. That's either one of these spots that I have at the start. And I want from that the group that was online. So I have to choose from these two options, and on the top I'm going to have online. So online and pass will be at the top of my fraction. I already have the probability of passing. I did that in this last problem. I found that from online and pass by doing 0.3 and 0.6. That's my first star. Plus not online and pass. That was the 0.7 times 0.75. When I'm trying to find the numerator, I'm only allowed to choose one of these two options. I'm only allowed to choose one of these two options. I want online and pass. That's up here. That's 30 times the 60. It's the 0.3 times the 0.6. I'm going to type this in and let's see what we get. And you might want to use parentheses on the bottom of that fraction. I get 25.5%. So if the student has passed a class, there is a 25.5% chance they took it online. I'm already starting to do part of what the goal of statistics is, which is based off of some information, predict what's happening for the future. So I knew something about these students, that they passed their class, and I'm now able to predict something about them otherwise, that they took it online. I'm going to continue to just practice stuff here, but these next couple of problems that we go through, no new material, just practicing probability and statistics a little bit more here. So suppose that I am wondering if there's a relationship between driving to campus and owning a TI-89 calculator. I decide to select two math classes and sample all the individuals in those classes. What sampling technique was used? Well, if I'm sampling, I have a whole bunch of classes, and I sample all the people in some of the groups, then this sounds like I am doing a cluster sample. Of the data collected, 70% drove to campus, 30% have a TI-89, and 90% have a TI-89 or drove to campus. What is the probability of having a TI-89 and driving to campus? Okay, so I want to look at the difference between this problem and the last one. And the last one, I had a whole bunch of those and out of blank statements. Whenever you have a bunch of conditional statements, it is easy to draw a tree, or at least easier to draw a tree. Whenever you have combinations of events with words like or and, you should think about doing table. So if you are given information about or and, you should think about making a table. And if you are given information for out of kinds of sentences, you should think about making a tree. This isn't a hard and fast rule, and as you practice, you might come up with your own kind of guidelines for going through things, but I hope this gives you a starting spot. I'm going to start this, and then I'm going to pause the video, and I'm going to have you finish this. 70% drove to campus, 30% have a TI-89, 90% have a TI-89 or drove to campus. I'm going to try to make a table. I have drive and not drive, and now I can just write complement to make that a little bit faster. And I've got TI-89 and no TI-89. And on the outside, I'm putting the total. I'd like you to pause the video and then give this thing a shot, filling in all of the numbers here, practicing this contingency table a bit more. So keep in mind, all of your probabilities should be adding up to 100%. Assuming you tried that out, let's fill in some numbers together. 70% drove to campus. So for the total for drive, I'm putting in 70%. If 70% drive, then that tells me the remaining 30% did not drive. 30% had a TI-89. So that must mean the rest, 70%, did not have a TI-89. This next part's a little bit tricky. I've not been given a problem with or before as a starting spot. Let's try to figure out what that means. 90% have a TI-89 or. This is the one that gives me more options. I'm going to highlight any spot that either has TI-89 or driving in red pen here. Or I'm going to do it with a check mark if you're comfortable. TI-89. These people have TI-89. They are part of the total. I am including them. Drive. They have drive. They already have a check mark. They have drive as well. So all three of these things are considered success, TI-89 or drive, or possibly both. And it looks like the only thing I don't have included is this one square here. I'll put a little box out. So the only thing I consider a failure in this situation is not driving or having an 89. That's not a failure in real life. Doesn't mean anything in real life. It's just in this specific example, it's the thing that we're not looking for. I know that all of the boxes together, that if I added the check mark total and that little box in the corner, that everything should add up to 100%. I also know that the OR total, that these three spaces add up to 90% in total. So I want you to pause the video and try to figure out if these three add up to 90 and they all together add up to 100%, how much does that leave me for this little box in the lower right-hand corner? And assuming you paused and tried that out there, I have 100% in total. These are 90, 100, take away 90, leaves me with 10% here in the corner. Let's use this to fill in the rest of the boxes. 20 and 10 gives me 30, so this must be a 20 here. 10 and 20 gives me 30, so that's 10. 10 and 60 gives me 70. 60 and 10 gives me 70. That's looking pretty good. So this problem asks for the probability of TI-89 or and drives. I got to be careful with the word and. That's where these things meet. Let's find that. TI-89 meets drive right there at 10%. So if I have information provided to me as or and, that's a table situation. If I have information provided as out of or given, out of those that take classes online, those are my tree situations. Second part of this problem asked me to create a contingency table with the given information. I've got a contingency table with that given information. I'm feeling pretty good about that. Calculate the probability that someone has a TI-89 given that they drive. Calculate the probability they have a TI-89 given they do not drive. I'm going to pause the video. I'm going to ask that you pause it as well and see if you can calculate those two conditional probabilities. Okay, so looking at this table some more, I've got the probability of TI-89 assuming they drive. So in the table, this is out of or divided by the group that drives. So it's out of that 70%. If I only look at that first column there, the amount of TI-89 that's inside of drive is 10 out of the 70. As a decimal, 10 out of 70 is 0.143 or 14.3% or so. Let's compare this to the probability of having a TI-89 if or out of those people that do not drive. So I'm looking at the second column, they do not drive. So this is out of that 30. Out of this 30, and I'm only looking at that column, the amount of TI-89 that exists is 20 out of 30. Rewriting this thing as a decimal, this is 0.66 repeating, or 0.667 if I can round a little bit, or 66.7%. So I'm noticing that if you do not drive, you are more likely to have a TI-89 than if you do drive. Are the events independent? Why or why not? Looks like there's a relationship. They're not the same ratios. So the events are dependent. If you drive, that's this first group, you are less likely to have a TI-89. We've now looked at how to do trees. We've looked at tables. We've looked at complement rules. We've looked at independence and dependence. There's a lot going on here, and I would encourage you to continue to practice, because just like learning a new language, it takes practice to really figure out these skills. So keep going, keep trying, and I'm here to help you out if anything comes up along the way.